I now have the honor and pleasure to introduce our next speaker. Dr. Moriah Sokolowski is an incoming assistant professor at TMU, or Toronto Metropolitan University, formerly known as Ryerson. She completed her MSc in 2015 and PhD in 2019 in developmental psychology at Western University and was a Banting postdoctoral fellow at the Rotman Research Institute at Baycrest Hospital from January 2020 to June 2023. Moriah's research program converges around one fundamental question: how does the developmental mind support complex learning? Because mathematical thinking is a learned skill that builds on both core competencies and previously acquired knowledge, it serves as an ideal model of how we learn complex problems. Dr. Moriah explores how the learning brain develops using diverse methodologies, including behavioral and brain imaging techniques in children, adolescents, and adults. In addition to conducting basic science, she's passionate about linking her findings to real-world outcomes to support individual well-being and population-level innovation. Thus, in a related stream of research, she explores how individual differences in core competencies, so visual imaging, spatial thinking, and memory, relate to real-world outcomes, meaning academic interest and occupational success. She uncovered basic building blocks of mathematical competency and identified early cognitive, emotional, and neural markers that relate to students selecting and succeeding in science, technology, and engineering mathematical disciplines. And her talk today is entitled The Building Blocks of Mathematical Thinking. Dr. Moriah, thank you so much. This is for you.
It doesn't matter. Thank you. And then the clicker. Sure, that's fine. Get in my pocket. Okay. Forward, backward, and laser. Okay, great. Thank you. Okay. Okay. Everyone hear me? Great. Well, thank you for inviting me. I'm really happy to be here today with all of you on this chilly Saturday to talk to you about the building blocks of mathematical thinking. Looks like I have a different title on here, but it's the same talk. So yeah, I'm Moriah Sokolowski. I'm an assistant professor at Toronto Metropolitan University. I've just completed 1 year as an assistant professor and starting into my second year. So I'm really looking forward to talking to you about my work today. So when I was in undergrad, I was doing my undergrad degree in psychology and was really, unsure what I was going to do, what I wanted to be when I grew up. And I did my honors thesis. So it's like the 4th year project that you do with Dr. Daniel Ansari. And through that project, what I did was I gave very young children an iPad intervention where essentially they went from not knowing anything about numbers. They were about 3 years old. That's me in undergrad with one of the children. And it was amazing. So I went in every morning at 9 a.m. We did like 10 minutes of work on this iPad where they learned their numbers. And over the course of the year, I watched these kids go from not knowing what a number was to, matching numbers onto quantities, knowing how to count, and even for some of them, basic arithmetic. And so I became really interested in this question: how does the developing mind support complex learning? And this made me realize that math is a really amazing model for studying complex thinking. It's one of very few skills that builds on itself. Infants don't know math. So I really love using math as a model to study learning. This is probably not a slide that I need for a room like this, but just very briefly, math is needed for essential life skills, whether it's, paying a tip at a restaurant, calculating how much flour you need in a recipe, although I will admit I have a tendency to sort of freeball it and then my baking is not great. In theory, I should be using math. Math ability is the strongest predictor of later academic achievement. And in a study in 2007, it actually came out as a stronger predictor even than reading and socioeconomic status in the Duncan 2007 study. And finally, math skills are needed for a growing number of occupations, particularly occupations in science, technology, engineering, and mathematics, or STEM occupations. Despite this, our students aren't doing well. in 2018, and then again in the most recent EQAO data, less than half of students in Ontario in grade 6 met provincial standards for mathematical thinking. So this is really concerning. I think we really need to focus on why our students are not reaching these provincial standards and what's happening long before grade 6 that might have cascading effects. And I think there's a few questions here. One is the kids who are really struggling. Why are they struggling? Those kids who are at the bottom, but also the kids who actually might be really well suited to go on and be mathematicians and maybe work here. What's going on there? Why are they not potentially reaching their full potential? So today I'm going to talk quite briefly about 3 streams of research that I've worked on in relation to mathematical cognition. So first, I'll talk about core competencies. Then I'll talk about socio-emotional factors, and then I'll just very briefly touch on some work that I'm doing looking at real-world outcomes. And if you have any questions, please feel free to stop me and ask, no problem. Okay, so let's talk about core competencies. So the question that I want to address in this section of the talk is, how does the developing brain learn basic numerical concepts? So the most basic numerical concept is understanding non-symbolic quantities. Understanding, if I ask you how many apples there are on that screen, you know, right? Or a couple of weekends ago, I went apple picking and I had a bag of apples and I stuffed it to the brim. Like apples were falling out of my bag. And there were other people who were very reasonable about how many apples they fit in their bag. And I knew that I had more apples than them, right? Without counting, using my non-symbolic abilities. This non-symbolic ability, the ability to estimate, understand, compare quantities, is something that we share with non-human species, so primates, but even bees, most recently Drosophila or fruit flies, have this non-symbolic understanding, suggesting that this ability is evolutionarily ancient. And there's some data suggesting that infants also have the ability to understand quantities. So if you show an infant 16 dots on one side and 8 on the other, using habituation looking paradigms, you can see that the infants look longer at the novel set of objects, suggesting that even very young infants have this ability. So it emerges early from an ontogenic perspective as well. In contrast, the ability to, if I tell you I have 3 apples without seeing these apples and understand what that means, or see this Arabic digit 3, this is something that's uniquely human and something that we learn over the course of enculturation and education. And so a lot of the work being done in numerical cognition has focused on, okay, how do kids, or how do we learn the concept of 3? The dominant hypothesis in the field has been that symbolic numerical abilities are essentially grounded in this non-symbolic system, right? We see 3 apples, we learn the word 3, and we map this word onto the 3 apples. This sort of starts to break down when you think about quantities like a million or a billion, right? This mapping, certainly when you say the word a million, I'm not imagining a million apples. So researchers started to question, is the symbolic system really just formed by a direct mapping of symbols onto the quantities that they represent? So for my PhD, I looked at this question in adults. So I'm not going to go through all the studies, but just to give you a sense, first I did a neuroimaging meta-analysis comparing all of the neuroimaging studies that have looked at symbolic number processing and non-symbolic number processing, and looking to see whether the brain regions that support both symbolic and non-symbolic number processing are common or distinct. Following this, I ran an fMRI adaptation study, trying to pull away everything that wasn't magnitude processing in a single sample of adults and understand, again, if you're looking at a set of numbers and you change one aspect of the number, how does the brain respond? So again, trying to understand whether the systems that support symbolic and non-symbolic number processing are overlapping or distinct. And finally, I developed a symbolic, non-symbolic Stroop task where, again, we're comparing either quantities or symbols and looking at interference between them to try and understand the automaticity of the processing of symbols and quantities. So I'd be really happy to talk about any of these studies. I never thought my PhD would end up as one slide, but here you go. But basically, the takeaway message from all of these studies is that in adults, symbols and quantities are processed distinctly, both behaviorally and at the neural level. And this is what I found through my work. A lot of other teams are finding the same thing. And over the course of the last 10 years, there's been a real shift in the thinking away from this dominant perspective that symbols are mapped directly onto quantities and towards the unknown of how do we learn symbols. So this led me to wonder, okay, so in adults, it seems that the symbolic and the non-symbolic system are actually quite distinct. But at some point, children have to learn the meaning of quantities, right? You have to learn that 3 apples, the word 3 represents them. So I became really interested in how children acquire these symbolic representations right at the beginning. So just a little bit of developmental psychology on this Saturday morning. So as I mentioned, infants have the ability to understand or process distinctions between quantities. Following this, I don't know how much time you've spent with a 2-year-old, but often a 2-year-old can count to 10 or can count backwards from 10 and blast off, right? This is a skill that you've probably seen. But if you ask that child, like, okay, great, what is 7? Like, they don't know. They're singing it more like a song, right? They're procedurally learning their numbers without conceptually understanding what those numbers mean. Around 2.5, 3 years of age, a child will learn the meaning of the number 1. So they'll understand that the number 1 represents exactly one object, and that can be applied to many different objects. About 6 months later, they'll learn the number 2. 6 months after that, the number 3, then the number 4, and usually around the time they're 4 or 5 years old, a child will learn the cardinal principle. The cardinal principle is the understanding that if you count a set of objects, the last object in your count sequence reflects how many are in that set. And once a child learns the cardinal principle, they apply it to all numbers. And so all of a sudden, you have what we would call a 4 number shifting, a 4 knower, shifting to being a cardinal principle knower or a CP knower. And they can, like, if I ask them how many objects are in this set, they can do it up pretty high as they can count. So that's what we know about the trajectory of how kids seem to learn these number symbols verbally. So I was really interested. I said, okay, so we have this knowledge about how kids learn their count sequence. And then we have this other idea that they have this non-symbolic understanding and maybe they're mapping it on. So what I wanted to know is, does symbolic number knowledge relate to children's spontaneous attention to numerical quantities in their world? So to address this question, first, I gave kids the give a number task. This is Daniel Ansari's son when I was doing my PhD. He's about 3 at the time, maybe 2. He was a 1 knower, although Daniel was pretty sure he was actually a 2 knower, and he wasn't thrilled that but it was fine. We all got over it. So this is how we assess kids' knower levels. Basically, that's a Dino puppet, and I would ask Leo, can you give Dino 2 blocks? And if Leo can successfully give Dino 2 blocks a couple of times and can't do the same with the number 3, Leo would be considered a 2 knower. So we had about 140 kids. We categorized them into their knower levels. We had at least 10 in each knower level group. And then I developed this new task called the build a train task. Leo was a big fan. He was very into trains at the time. And the way that this task works is essentially I build this train using my blocks. And you can see that my blocks are longer than Leo's blocks. And I say to Leo, make your train the same as mine. And then Leo uses his blocks that are a different size to match the train. And so you can see here, this is a reasonable match. He's using 3 small blocks and I'm using 3 large blocks. So here he could match my train using a number strategy. Whereas here, if numerical information is not as salient, he also could match my train using a size strategy. So it's a non-directed task where we're just interested in, are you thinking about quantities in your world right now? Any questions on this task? Okay. Yeah. You have to do it twice, like were these two different testing or? Yeah, so it's a great question. So we had 16 trials with a bunch of different train lengths and different blocks where sometimes his blocks were smaller than mine, sometimes they were bigger than mine. And we had it for numbers 1 to 5. Yeah, great question. Thank you. So this was actually, I think, the same trial where we thought he was going to use a number strategy. Daniel got pretty excited, and then he put the size. A lot of the children too, just want to build the longest train. So the data is very messy. But I'll show you what we found, or a bit of what we found. So this is the data from one knowers. So these are children who only know the number 1. And just to orient you to this graph, along the bottom is the train length. So whether I use 2 cars, 3 cars, 4 cars, that's on the bottom. On the y-axis is the frequency of strategy. So in blue is how many times out of the 16 trials they use a number strategy, and in red, how many times they use a size strategy. So you can see the one knowers, they're not doing much. They're mostly building the longest train possible, to be honest, and not really engaging always in the task. They're also about 2.5, so attention span is short. The two knowers, though, they are using a number strategy more than a size strategy, but only for the number 2. So only for numbers that they already have learned the verbal number word. 3 knowers are using a number strategy more than a size strategy, but only for numbers 2 and 3. So we see this really interesting pattern where learning verbal number words actually corresponds with how children are interacting with their world and how they're thinking about quantity in their world. So essentially in this section, we've rejected the dominant hypothesis in adults that symbols are mapped directly onto quantities. But we do find that there is certainly some link between learning verbal number words and thinking about quantities in our world. But what this data can't show is whether there's this underlying representation of quantity that comes online right as a child is about to learn the symbol, or if learning a verbal number word actually acts as an attentional scaffold and helps children understand quantities in their world. So my grad student is actually in the process of starting a microgenetic study where we test kids every week to try and see if it's a cause or a consequence. So maybe in a year or something, I can tell you the answer to this cause and consequence. But all this to say, the emergence of these core numerical skills that are foundational for later mathematical thinking, it's complicated. And the way that we learn these symbols seems like some sort of dynamic interplay. So that's the core competency section. I also want to talk about socio-emotional factors. So children, humans, we're not mini computers, right? We talk a lot in cognition about these hot versus cold processes, and cognitive mathematics is no different, right? We have feelings and emotions about doing math. And so the question that I want to talk about in this section is, why do females tend to have more math anxiety? So a lot of people, often as much as 20% of a classroom, experiences fear and apprehension when doing mathematics. This is an article that I wrote for Frontiers for Young Minds. It's this really great journal where it's sort of common topics in neuroscience, but also math, physics, that the articles are written for children, and they're also reviewed by children. So it's a child and a scientist who co-review these articles. So they're really great. If you have like a 10 to 14-year-old who's interested in science, I would highly recommend going to this Frontiers for Young Minds website. So there's a lot of research going on right now about who's afraid of math anxiety, what it is, and what we can do about it. So was interested in this question of why we see such higher rates of math anxiety in females compared to males. So as a side project, when I was working and doing my PhD, I thought, okay, let's look at cognitive, neural, and socio-emotional predictors of which students are likely to enter and succeed in STEM courses in their undergrad degree. So it was pretty straightforward. We stood outside big first-year classrooms with big signs and invited students in their first semester of their first year of undergrad to come and participate in our study. We gave them a large battery of cognitive tests. We put some of them in an MRI scanner to get some neural information. And then we also measured social emotional questions. So this is data just from that. Oh, and then one other thing we did is over the course of their undergrad trajectories, they sent us their transcripts. So we got the courses they took, the grades they got in them, whether they switched their major. And then the plan has been, and we've been working on this, to use cognitive, emotional, and neural data to predict all kinds of information from academic transcripts with a focus on mathematical thinking. So these data I'm going to show you is just from time one. So we were interested in this question of the relationship between biological sex and math anxiety. So again, in this sample, we found females report much higher levels of math anxiety than males. And our first thought was, well, maybe it's because of math ability, right? So we ran a mediation model where essentially we looked at whether math ability explains the relationship between sex and math anxiety. And in short, it didn't. So we thought, okay, maybe we're thinking about this the wrong way. Maybe it's not actual math anxiety, because we actually see that in terms of actual math ability, there's very few differences in actual math ability between females and males. So we thought, okay, maybe it's, oh, it's not popping up. There it is. Maybe it's perceived math ability. So we tried this as well. And again, this was not significant. Oh yeah, there we go. Gender similarities characterize math performance. That's what we find. They're way more similar than different in performance. So that's why we tried perceived math ability. But again, it didn't mediate this pathway. So then we started thinking, okay, what's going on here? It's not math ability. It's not perceived math ability. What could it be? So we went back to the literature. I chatted with Zach Hawes, who's an expert in spatial thinking. And what we noticed is that a lot of the sex differences we see in representations of number actually seem to come from ways of mathematical problems that rely on spatial thinking. And we do see that spatial cognition, or the ability to mentally manipulate something in the mind's eye, is one of very few cognitive skills that males consistently outperform females at. So we thought, okay, maybe there's something going on with spatial thinking that's mediating this association. So we went back to the drawing board, and now we put in spatial ability. So the ability to mentally rotate an object using sort of a standard block task from like the 1950s. Perceived spatial ability, so whether you think that you're good at this, and also spatial anxiety, so how anxious you would feel having to do this task. And now, each of these three alone did indeed mediate the association between sex and math anxiety. And then when we put them all into the model together, spatial anxiety explain the most variance in the relationship between sex and math anxiety. So what does this tell us? Again, it's complicated. It tells us that, just looking at core competencies, which I must admit I love to do, doesn't explain the full picture of what's going on with mathematical thinking across the lifespan. There's socio-emotional factors that are coming into play. So different like hot versus cold processes, but also influences of other cognitive factors, such as spatial thinking. Like space seems to matter. And so we really need to be thinking about both different levels of analysis and also across cognitive domains to understand the building blocks of mathematical thinking, as well as individual differences in mathematical thinking. So finally, I'm just going to very briefly touch on real world outcomes. I spent a 4-year postdoc looking at this question at Baycrest Hospital, and I, just for the sake of time, won't be able to get into all that data, but I mentioned that we had the transcript data, and I thought you might want to know what we predicted with that. So I'm just going to very briefly touch on this question. Does math ability and or math anxiety predict which students are going to select and succeed in STEM courses in their undergrad? So this is a plot of the number. So on the left is the number of STEM courses that students take across their 4-year degree, again at Western University. And on the right is the grades that they get in those courses. Here we have 0-order correlations. So, unsurprisingly, they're in different directions because high math ability. So when you look at them alone, not together, high math ability correlates strongly with the number of STEM courses that students take, that's that yellow bar, and how they're doing in them, again, the yellow bar on the right. And math anxiety correlates negatively with, again, the number of STEM courses they take and how they're doing in them. So not surprising, right? Students who are good at math and have low math anxiety are more likely to select and succeed in STEM courses in undergrad. Interestingly, when we put both math anxiety and math ability into the same model, math anxiety wins. Math anxiety accounts for all the variance that we're seeing in math ability and becomes the strongest predictor of which students are most likely to select and succeed in math in STEM courses in undergrad. So following this, I looked into other non-traditional predictors of who's going to select and succeed in STEM. So I'm currently looking at things like spatial imagery, static versus dynamic imagery, those sorts of things to try and understand the full picture of who's going to select and succeed in STEM. That's another talk, which I'd be happy to give another time. But for now, I just want to highlight that both ability and anxiety does seem to predict, but anxiety uniquely and more strongly. That's all I'm going to say about real world outcomes, although it's an area that I'm really interested in now. So just looking ahead to the future. So I've completed 1 year as an assistant professor at Toronto Metropolitan University. I've launched the Neuroimaging Development and Educational Attainment Lab, or the NeuroIDEA Lab. And in that lab, we're looking at a lot of these questions. So we're looking at trajectories of symbolic, non-symbolic thinking, as well as non-numerical thinking. What's the role of symbols, quantities, but also understanding of space, understanding of size. How do they emerge across developmental time? How do they interact with each other? With the plan then to look at how these systems predict later higher level mathematical thinking, the role of social emotional processes in these relationships, and also starting to look at these associations at the neural level. In the far future, I'm really interested in understanding how the link between cognition and mathematical cognition and real world outcomes differ from kids from diverse backgrounds, and identifying ways that we can support all children identify and succeed in their ideal academic niches, whether that be in STEM or in other disciplines. So with that, I want to thank, that's my new lab in the middle, my PhD lab on the right, my postdoc lab on the left. I want to thank both my mentors, all my collaborators, the research assistants who collected all these data, funding, and thank you for your attention.